Hey folks, good afternoon. So today we're going to tell you a little bit of a story about what we've done at LexisNexis with A/B testing, where we've deployed a technique to really accelerate our testing program. It's made a huge difference to our capacity and our capability to drive optimal improvements right across all of our products and websites. It's a technique so powerful that in the short case study we'll show you today, the test itself would, under normal circumstances, have taken over a decade to get to a confident result. Now it takes us a matter of weeks. We call it neo-Darwinian testing, largely because I'm quite pretentious. But for the sake of telling this story, because the evolutionary principles that connotate actually have a key role. So I'm just going to set you up with a little bit of context before the brains behind it take you through. Is the clicker working? That one. Thank you. So a quick bit of context about setting up a program. Many of you may already have come across these challenges, but it's just to set the tone. And again, I like the evolutionary theme. It explains it. And specifically what I set out to do was to extinguish or make hippos and rats extinct. Not in a sociopathic sense, but you probably get where I'm going with this. We wanted to get rid of hippos and rats. And most of you probably know what hippo means, the highest paid person's opinion. Jobs being a classic example of it, although it's fair, he was pretty good. And a rat in our world means a random act of testing. And again, you probably come across that a lot as well. This was from another company. I hasten to add, not Lexis, but I got that quote the day after launching a new website. 6 months of user research, testing, A/B testing, it was working, but CEO's wife didn't get it. We should go back and look at it again. Classic hippo, and he wasn't taking no for an answer. So based on that experience, what we wanted to go ahead with was go in and get rid of these particular cultural issues. And a random act of testing, incidentally, will be something like, oh, this customer in Chicago likes red buttons, and this customer in New York likes blue. We should test that. That's not a test. Now, to get rid of that, you've got to get in very, very good, strong KPIs. Some people call it the one metric to measure. And once you get those in and you can build solid plans around that and good hypotheses, the program starts to take a push of its own. For those of you who are squeamish, I apologize for the coming slide, but it's a brilliant real-world example that really takes us forward. I actually took that photo. It's Schiphol Airport in Amsterdam, and it's a case study I found about afterwards, because I couldn't figure out that it's actually a cute little fly on the urinal itself. And what Schiphol did, it's a massive hub airport. And they were having to clean their toilets every 20 minutes. It cost an absolute fortune. So what they did is they put in proper goal. We need to lower our cost of cleaning, and they found the right KPI to align to that goal. In this case, spillage rate. And they came up with a hypothesis, in this case, based on an observation that men are pathetic, and we will aim at things. And it worked. Check out how much they saved. And to me, I always use this as an example. When you're explaining A/B testing to people, they think it's something funny on a screen. It doesn't. It applies to the real world as well. Get the metric in place, get a good hypothesis, find a good way of testing it. Despite doing all those things, this was still me a couple of years ago, because some of the bigger companies that run this and do it, like Amazon, can run A/B tests. I think I've seen in about 40 minutes flat. They can get a confident, secure A/B test and a result and push it to production in about 40 minutes, which I'm hugely envious of. Bastards. But mostly for us, so things like traffic limitations, trying to get the right A/B tests in place, trying to build it out, the complexity of trying to do multivariate testing with finite traffic samples and stuff, we weren't getting the momentum we needed. I think in the first year on the product, we only pushed 4 of our tests live. It's not the sort of momentum you need. You want to be orders of magnitude above that. Enter these two guys.
Great, thank you, Steve. So I think most of us are aware of what A/B testing is. Obviously, there are typically two designs. The incoming traffic is divided into 2 sections. One of them sees the version A, the other one sees the version B. There's a KPI that you're measuring. One of them gets some more sales, for example. If that's the KPI, that becomes your design, and then the process continues. So that's a very simplified version of the A/B testing. Now, obviously, with this, there are certain key issues that we need to address, key challenges. Number one, obviously, is the slow speed. So if you have one or few changes, obviously, it takes a lot of time for it to kind of take effect if you have many changes. That's number one. The other thing, which I think is a bit more important, is that this is a very classical greedy approach to optimization. So what you're doing actually is you're always going for the best option. So it's a greedy algorithm, if you will. Eventually, those kind of algorithms, those kind of approaches leads to local optimum. And that is one of the key challenges as well. And we'll see an example of that. So let's suppose we are wanting to test a button, and there are two things that we can change: the color, either red or blue, or size, either small or large. And what we want to do is obviously achieve an optimum design. So we could start with one. Let's say we want to test the color. We have a blue variant and a red variant. You see the KPI with red is better, so obviously we'll adopt that. Red has a 6 KPI. Then once that is adopted, again a very greedy approach, that has been approved, adopted, we then test for the size, right, large or small. It turns out large has a higher KPI, it is 8, so that's the one that needs to be adopted, and then the process kind of continues with A/B testing. But what we have not realized over here is this: if we would have gone with the blue option first, we would have achieved a higher optimum. And that's an example of a local optimum, wherein the red and the large leads to a local optimum, but the other one is a global optimum. Now, people who are familiar with these kind of things, they would notice that we could always do a multivariate testing. In a multivariate testing, what happens is you can actually have, you can see, hey, there are 4 combinations here. So why just have 2 options? Let's have 4 options, right? And the incoming traffic can be divided into 4 kind of buckets, and that would work. You will achieve a better design, you will achieve a local global optimum. So instead of a local maximum, with multivariate testing, you are going to get a global optimum. But there are challenges with multivariate testing as well. What if there are more than 2 options, or there are more than 2 changes? What if you want to make 12, 13, 15, 20, 50, whatever number of changes? So this is a hypothetical example. There are 9 changes over here that I want to make. Each one has 4 options. Just imagine red, blue, green, whatever color, size, font, etc. Right? There are 9 things that we can change. It turns out the number of combinations are 262,144. That's 4 to the power of 9 in a very simple way. So that's the number of combinations there are. So how do we even begin to test this? So it's just not about dividing into 4 traffic. It's about division into 262,144. So that is what makes this multivariate testing approach at scale just improbable or impossible to achieve. So what do we do?
Whenever I'm doing strategy decks, I like to slip in, just to keep myself amused, random film references. So what you're looking at here, for those of you struggling to work this out, that's Darwinism plus artificial intelligence equals nirvana. It helps to explain these things when you're dealing with executives, but again, hopefully this is going to become clear to you now without the dingbat.
Great.
Over to you.
So evolutionary computing, and that's what we've done. We've actually implemented a version of the genetic algorithm with, to achieve, let's say, a better optimum. Obviously, global optimum might not be possible, but a better optimum than a local optimum. So the way it works is initially you can have a multivariate instance of, say, 8 to 10 or 15, 20, however many different designs to start off with, and that's the first column on the left. Over here in a simplified example, you have blue, purple, green, and red. Each, because it's a multivariate test, each of them is also being tested for that KPI, whatever that KPI is that you're testing for, and that's the result that you're getting, called medium, low, high, medium, meaning that some variants are actually doing well, some of the variants are not doing so well. The next stage, obviously, is the reproduction and the mutation stage. So what happens is, and what you'll see over there is that the purple one doesn't get a chance to get selected. So the purple one gets dropped off. Again, this is more of a survival of the fittest because the performance is very low. And the other thing you'll notice is that green, actually, the green variant has 2 copies there. And the reason is because green is highly fit. So green gets more chance to reproduce. So green-blue becomes blue-green and green-blue, and green-red then made together to become two offsprings, red, green, and green, red. And that, again, a new set of multivariate tests. You launch those, you find out which ones are doing well, and this cycle just continues. So that's basically how the approach is in terms of combining genetic algorithms with, with the A/B testing. Thank you.
Thanks, Vaqar. So we started to perform a pilot on our US e-store. So many of you may know LexisNexis is a legal research tool, but we actually also sell books. Some of the books we sell are on landing pages like this one that actually you can go in and you can purchase, I know it's an anathema, but an actual physical book, and we will ship it to you over the internet. No. Anyway, so the goal here is that, yes, people will buy books over the internet, and our job was to figure out how we can sell more books over the internet. So our hypothesis was that by using this testing methodology, we'll be able to iterate much more quickly on designs and come to a global maximum much more quickly than we would if we tried to do a regular multivariate test or a traditional serial A/B test. All right, so population and gene pool. OK, I'm sorry, this is a bit of an eye test, so let me just talk you through it a little bit. We have all of these different features that we want to optimize, or that we could optimize. So add to cart color, add to cart label, add to cart icon design, detail label, so on, so on, so on. The blue row right there represents what our control conditions were. So the initial add to cart color was the color blue. And then we wanted to also test the add to cart button color red, green, orange. The total number of possible combinations here is 184,320. It would have taken us dozens of years to actually run this as a multivariate test with our store's traffic levels. If we were to do this serially, there's just no guarantee that we would have come to a global optimum. So what are we going to do? We're going to apply this genetic algorithm methodology. So the way that we did this was that we ran the test in multiple waves, and we iterated on the genes for the test after each wave. So the way that this would work was the first wave, we had 50 different genomes. That's 50 different combinations of variables. So with that, we got 5,000-ish views with 3,000-ish visitors. And we saw an increase of about 2% of this add to cart metric. We ran that for only 7 days. And then we pulled a bunch of the genomes out. They were not fit, right? So we just cut those ones. And then the ones that were fit, we combined those in new and interesting ways so that we could start to get more signal, as Vaqar was talking about earlier, so that we're actually doing that mutation. All right, so then we ran 30, and we ran those 30 genomes for another, I think, what, 5 days? 3 days. The next one did the same thing again, 5 days. The next thing, same thing again, 7 days. The next thing, same thing again, we ran for 21 days. By this point, we're actually seeing another couple percent lift. And then we ran the sixth wave, and the sixth wave was our final wave. We ran that with 40,000 some odd views over 40 days, and we saw another couple percent lift in add to cart. So totals, in all, we actually ran through 162 genomes, used roughly 100,000 views with 60,000 visitors over 83 days. So that might not seem like it's very short, but if you consider the number of genomes that we ran through, that's 162 different variants that we ran through so basically we ran through 2 a day. So what did that look like for our KPI? We've got cumulative daily clicks represented here. The flat lines indicate that those genomes were cut. So as we went on through this final iteration, you can see that the highest performing, somewhere there's a laser, there we go, our highest performing variant here is really starting to outpace our control, which is this line here. And we see kind of a cluster of other variants that are also performing pretty well. So details of that last wave. So this was our highest performing variant here. If we can see here, the lift was about 20-something%, depending on which metric we look at. And we can also see that the other 3 variants here were also performing similarly much better than control. So why is that? It turns out that the top 3 variants actually had a lot of similarities to them. So this wasn't just a statistical fluke. There is something that is actually an improvement about having the cart color be green, right? All of those variants had this green cart color. They all had this same like international order box. So all of those things seem to be driving performance that improved each of those over control. So clearly this isn't a fluke. This is something that actually each of these add value, but there are differences between them that allowed this top performing candidate to really differentiate itself from the other two and way, way, way above control.
Random movie reference. How best could I convey taking a genetic milkshake and optimizing it to make something special? That's the best I could come up with. If anyone's got any better suggestions, please do let me know. In terms of what we're doing next, Mr. Rubinstein.
Yeah, so what we're doing now, we have an in-house A/B testing platform that we developed. It's called Abe. We are integrating the genetic algorithm into Abe so that we can actually start to optimize our search algorithm. The search algorithm has 40 some odd levers. The number of possible combinations is something like Avogadro's number. So it is a really, really large number of possible combinations given just the sheer number of levers and the number of values that we could have for each of those levers. So you can kind of see how we are integrating that down here at the bottom. So there are values that are like activity score disabled or activity score 4.5 something, something, something. So there are all of these different values for each one of those levers. So we end up with just a massive combinatorial explosion of possible variants. So this is a great chance for us to actually use the genetic algorithm to do the optimization just because the feature space is so large. We would just never be able to do this in a multivariate way. And to do this in series is kind of how we got to where we are now, which is a very good search engine. But could it be better? Probably, right? We don't know that we've achieved some global optimum, but we're pretty confident in our current local optimum. But maybe there's a bigger mountain that we'd like to be on.
Makes sense. So hopefully the combination of facetious film references and the science that the guys have just taken you to has given you some context of what it was. But we've left some time for questions because I think the devil is in the detail. That said, because of this, we've suddenly become very popular, Ellen, and James wouldn't forgive me unless we gave out this note as well.
Yeah. We are hiring. We're hiring data scientists, data engineers, data analysts, and software engineers. So if you're interested, we're out of Raleigh-Durham, North Carolina. So come through beautiful Raleigh. And yeah, anyway, so be sure to hit me up. You're welcome to hit me up on LinkedIn or ping me with an email. Happy to hear from any of you. And now we can take some questions.
Now we can take questions.
So can you comment on like your A/B testing framework in the context of personalization, right? Like you're talking here about kind of creating like optimized user experience for, but I believe from what you described, it's really intended for general audience, right?
That's correct.
Have you considered this in the context of like basically personalized content given certain user segments, right? And when you do so, can you maybe also comment on like how this was compared to like other similar A/B testing frameworks, like for instance Netflix uses like bandits for personalization?
Yeah, so personalization. No, there's an easy answer there. No, we're not doing personalization. That's not taken into account. This is sort of the best for the most kind of A/B testing strategy. Multi-arm bandits, this is kind of a different approach than multi-arm bandits, which are kind of similar, but you would still have to have every possible combination, and then you just sort of greedily give more traffic to the one that is doing better. We're still trying to get to a global optimum that we can then test against with like statistical confidence. You could do the same thing with bandits, but it might take rather a long time.
One thing I would just want to add on that, on a multi-arm bandit problem, you don't have reproduction, and you don't have crossover, you don't have mutation, you don't have selection. Those genetic operators are not there. So what's happening is as the traffic is coming in, what you're doing is you're just diverting it to the one that has the highest performance, and the one that but the one that has the highest performance doesn't combine with anybody else on any other variant. So it's just you're just diverting the traffic in a way. With genetic algorithm, you have an advantage of the multivariate, arm bandit problem, issue as well. But at the same time, it's also recombining with the best possible, outcome. So that's where the difference is.
The other hook is with the internal testing tool, we've got far more advanced analytics now. So after the event, as we're running a test for, say, a month, even 2 months, we can retrospectively go back and look at a granular level at the segments behaving and specific clusters as they come in. I'm more interested in clusters of user behavior than actual segments at the moment, which is one of the reasons we're not looking at it. It's an option, but at the moment, no.
So my question is about the initial seeding of the genomes, right? Because obviously there's a wide array of possibilities, but you started with 50. So are those just randomly selected, or were they, say, selected for maximum diversity, or how was that seeded in order to get the best outcome?
I think that's a good question. So I think one criteria is the number of traffic that you're getting. So for example, if you're getting in millions, for example, you might even go with 100 or 200. You can go with a larger population size, for example. So that was the key criteria for us. The other thing is, I think it's also interesting, and that's what we found useful, is that we seed the initial population with some of the variants that are heuristically doing well or have done well, so involving the experts, if you will. But there is a certain segment of the population which is completely random as well, just to make sure that we don't lose out on those possibilities. But to be honest with you, this is all a heuristic approach. There's no optimum approach to select the size of the population in a genetic algorithm environment. So these are some of the heuristics we use to do that.
Yeah, there's a little bit of art in the science. For that particular pilot, there was a lot of UX heuristic research that went in. A lot of that was to get rid of the rats. And I think one of the things I liked about this is we could actually include them pretty quickly. I think there's another deck we've got which showed our branding people insisting that everything should be red, naturally. Red died out really, really quick. Just gun to the head, gone within two. And because it worked. And and people who do testing a lot, it's because the buttons stand out more. That's the reason why red just blends into the rest of the branding. But it's a really powerful way of going, well, okay, we tried it. But it's quick, so you don't get a wasted test, which I like.
Can you guys talk a little bit about what happened between each wave in terms of the research and iteration to set up the next wave?
Yeah, so basically what happens is that in each of the wave, you have an evaluation function, which actually is the performance of the KPI that you're tracking. And then once you have that confidence in terms of how they have performed, say over a week, 8 days, however many days that you need, then the genetic algorithm actually combines the ones that are performing at a very high, with high evaluation scores. So that's where the reproduction and the mutation happens. Basically, it's about combining two designs with taking elements from one and then taking elements from the other one. And then that combination creates obviously new designs. So you do that successively over many generations. And what happens is the best ones start to, or the best components start to emerge, because they're the ones that combine and give you higher lift, and then eventually that optimum level is reached. And then eventually what happens is that no further improvements are noticed. And you could see that line that, and then that's when you feel that, hey, you've reached, near optimum kind of results. So that's what happens in between.
Cool. There's a question over there.
Is there like a paper that you guys referenced for this? I'd love to learn more about it. Are there like any documents or anything like that?
Yeah, we are in the process of writing a white paper on this. Hopefully, one of the things we wanted to do was the test that James just talked about, the search test that we want to do. And hopefully, yeah, so we don't have a white paper as yet, but that's in the plans at the moment. So the best thing you can do is contact James with that.
Do you do like theoretical guarantees for like how long it takes to reach like a global maximum?
No. Again, that's somewhat heuristic. We just kind of have to run it and see how it goes.
Right.
So, okay.
Right.
Do we still have time? Or? No? Okay, I think we're out of time. You are welcome to reach out to me over email. Thanks very much.
Great, thank you.